Imagine you are trying to find the highest or lowest point on a hilly landscape, but you are forced to stay on a curved path, a road, a fence line, and so on. The Lagrange multiplier theorem tells you a necessary condition that any such best point must satisfy. Mathematically, let's f of x sub 1 x sub n be the function you want to optimize height, cost, profit, and so on. G of x sub 1 x sub n equals 0 be an equality constraint, the road you must stay on. If x star is a point where f attains a local maximum or minimum subject to the constraint, then there exists a number lambda, the Lagrange multiplier, such that nabla f of x star plus lambda times nabla g of x star equals 0, and g of x star equals 0. In words, the gradient of the objective function at the optimum is a scalar multiple of the gradient of the constraint. The gradients point in the directions of steepest increase. The condition says the two directions are collinear, which is exactly what you expect when you cannot move off the constraint surface. The theorem gives only a necessary condition. Any candidate point must satisfy it, but not every solution of the equations will be a true maximum or minimum. Further checks are needed, second-order conditions. Explanation: building the Lagrangian and getting the first-order equations. 1. Create the Lagrangians. The Lagrangian combines the objective and the constraint using a new variable, the multiplier. L of left parenthesis x sub 1 comma x sub n comma lambda right parenthesis equals f of left parenthesis x sub 1 comma x sub n right parenthesis plus lambda g of left parenthesis x sub 1 comma x sub n right parenthesis. If there are m constraints g sub k of x equals 0, add a term lambda sub k g sub k of x for each. 2. Differentiate. Take partial derivatives of L with respect to every original variable and each lambda. Partial of L with respect to x sub I equals 0, for I equals 1 through n. Partial of L with respect to lambda equals 0. The first set gives the gradient condition nabla, f plus lambda nabla g equals 0. The second set simply reproduces the original constraints g of x equals 0. 3. Collect the equations. You now have n plus m equations with n plus m unknowns, the x sub i's and the lambda sub k's. Solving them yields all stationary points that respect the constraints. The Lagrangian can be thought of as a balance sheet. The original objective is the profit. The constraint terms are like penalties that become 0 when the rule is obeyed. But their coefficients, the multipliers, tell you how much the objective would change if the rule were relaxed a little. For each variable x sub I, you have an equation of the form partial f partial xi plus sum from k equals 1 to m of lambda sub k times partial g sub k partial xi equals 0. For each constraint you have g sub k of x equals 0. Often the constraint equations are simpler than the gradient equations. Solve the constraints for one or more variables and substitute back into the gradient equations, removing the lambdas. Alternatively, treat the multiplier equations as linear in the lambda sub k, gather them into a matrix form del f plus j transpose lambda equals 0, where j is the Jacobian of the constraints. If j has full rank, you can solve for lambda equals negative j transpose inverse times del f and then plug into the constraints. After eliminating the lambdas, you are left with equations only in the x's, typically nonlinear. Solve them using substitution, factoring, or numerical methods if needed. Every solution of the algebraic system is a candidate. Keep the ones that also satisfy the original constraints. Use second-order tests, bordered Hessian, or evaluate the original function to decide whether each candidate is a maximum, minimum, or saddle point. In practice, for small problems you can often solve by hand. For larger engineering problems, you would feed the equations into a symbolic solver, MATLAB, Mathematica, Python SIMPy, and let the computer handle the elimination. Imagine you have a set of balance scales, the equations. The multipliers are the unknown weights you need to put on the side of the constraint scales so that the whole system stays in equilibrium. By solving the scales, you find both the position, x, and the necessary counterweights, lambda. Problem statement. Maximize the profit function f of xy equals 3x plus 4y, subject to the resource limitation g of xy equals x squared plus y squared minus 25 equals 0, which says the total amount of raw material used must lie on a circle of radius 5. Step 1. Form the Lagrangian. Script L of xy lambda equals 3x plus 4y plus lambda times open parenthesis x squared plus y squared minus 25 close parenthesis. Step 2. First order conditions. Partial L of x equals 3 plus 2 lambda x equals 0, so 2 lambda x equals negative 3. Partial L of y equals 4 plus 2 lambda y equals 0, so 2 lambda y equals negative 4. Partial L of lambda equals x squared plus y squared minus 25 equals 0. Step 3. Eliminate lambda. From the first two equations, lambda equals negative 3 divided by open parenthesis 2x close parenthesis, which also equals negative 4 divided by open parenthesis 2y close parenthesis. So 3 over x equals 4 over y, which gives 4x equals 3y, therefore y equals 4/3 x. Step 4. Use the constraint. Substitute y equals 4/3 x into x squared plus y squared equals 25. This gives x squared plus open parenthesis 4/3 x close parenthesis squared equals 25. Simplifying x squared plus 16/9 x squared equals 25. Combining terms 25/9 x squared equals 25. Thus x squared equals 9, so x equals plus or minus 3. Correspondingly, y equals 4/3 x, which gives y equals plus or minus 4. Step 5. Evaluate the objective. F of 3, 4 equals 3 times 3 plus 4 times 4, which is 9 plus 16 equals 25. F of negative 3, negative 4 equals negative 9 minus 16 equals negative 25. Thus the maximum profit is 25 at the point 3, 4, and the minimum is negative 25 at negative 3, negative 4. Real-world picture. The constraint circle could represent a fixed amount of total material, for example 5 kilograms. The profit line says each kilogram of product A gives $3, each kilogram of product B gives $4. The optimum is to use the material in the ratio 3:4, exactly hitting the material limit. Verification of first-order condition. At the point 3, 4, the gradient of f is the vector open parenthesis 3, 4 close parenthesis, and the gradient of g is the vector open parenthesis 2x, 2y close parenthesis, which equals open parenthesis 6, 8 close parenthesis. Indeed, the gradient of f equals 1/2 the gradient of g, so lambda equals 1/2. Problem statement. Minimize the cost function f of xyz equals x squared plus y squared plus z squared subject to g1 of xyz equals x plus y plus z minus 6 equals 0, and g2 of xyz equals x minus y equals 0. The first constraint forces the sum of the three quantities to be 6, for example the total length of 3 rods. The second says the first 2 rods must be equal in length. Step 1. Lagrangian with 2 multipliers. Lagrangian equals x squared plus y squared plus z squared plus lambda 1 times open bracket x plus y plus z minus 6 close bracket plus lambda 2 times open bracket x minus y close bracket. Step 2. First order conditions. Partial L with respect to x equals 2x plus lambda 1 plus lambda 2 equals 0, equation 1. Partial L with respect to y equals 2y plus lambda 1 minus lambda 2 equals 0, equation 2. Partial L with respect to z equals 2z plus lambda 1 equals 0, equation 3. Constraint 1, x plus y plus z equals 6, equation 4. Constraint 2, x minus y equals 0, equation 5. Step 3. Use the simple constraints first. From equation 5 we have x equals y. Insert into equation 4. X plus z equals 6, which gives 2x plus z equals 6, so z equals 6 minus 2x. Step 4. Express multipliers in terms of x. From equation 3, lambda 1 equals negative 2z, which equals negative 2 times open bracket 6 minus 2x close bracket, giving negative 12 plus 4x. From equation 1 and using y equals x, 2x plus lambda 1 plus lambda 2 equals 0, so lambda 2 equals negative 2x minus lambda 1. Plugging in lambda 1, lambda 2 equals negative 2x minus open bracket negative 12 plus 4x close bracket, which simplifies to 12 minus 6x. Check with equation 2, 2y plus lambda 1 minus lambda 2 equals 2x plus open bracket negative 12 plus 4x close bracket minus open bracket 12 minus 6x close bracket, which simplifies to 12x minus 24. Setting this to 0 gives 12x minus 24 equals 0, so x equals 2. Step 5. Find all variables. X equals y equals 2. z equals 6 minus 2x, which is 2. So the only stationary point is the point 2, 2, 2. Step 6. Evaluate the objective. F of 2, 2, 2 equals 2 squared plus 2 squared plus 2 squared, which is 12. Since the cost function is a sum of squares, it is always non-negative and grows as the variables move away from the origin. The constraints force the point onto a line where the sum is 6. The point 2, 2, 2 is the closest to the origin, hence it is the global minimum. Real-world analogy. Suppose 3 machines must together run for 6 hours per day, and the first 2 must run the same amount. We want to minimize the squared operating time, a proxy for energy waste. The answer tells us each should run 2 hours. Verification. Gradients at the point satisfy gradient f equals 4, 4, 4, and the constraint gradients are gradient g1 equals 1, 1, 1, and gradient g2 equals 1, negative 1, 0. Indeed, gradient f equals 4 times gradient g1 plus 0 times gradient g2, corresponding to multipliers lambda 1 equals 4 and lambda 2 equals 0, consistent with the earlier calculation after scaling. The first-order conditions only tell you that a point could be an extremum. To know whether it is a maximum, minimum, or a saddle, you examine the curvature of the Lagrangian restricted to the constraint surface. Build the ordinary Hessian of f colon hf equals the matrix of second partial derivatives of f with respect to xi and xj. Compute the Jacobian matrix J of the constraints. Each row is nabla G sub k. Form the bordered Hessian B colon. B equals a block matrix with a zero block of size m by m in the upper left, J in the upper right, the transpose of J in the lower left, and HF in the lower right. The upper left block is a zero matrix because the second derivatives of the constraints with respect to the multipliers are 0. Evaluate determinants of the leading principal minors of B of order m plus 1, m plus 2, up to m plus n. For a local minimum, the signs must alternate starting with negative 1 to the power m, that is, negative 1 to the m times delta sub m plus 1 greater than 0, negative 1 to the m plus 1 times delta sub m plus 2 greater than 0, and so on. For a local maximum, the signs must follow the opposite pattern. If the pattern fails, the point is a saddle or does not satisfy the second-order conditions. Think of walking on a hilly terrain while being forced to stay on a tightrope, the constraint. The bordered Hessian measures how the terrain curves along the tightrope, ignoring directions you cannot move in. Positive curvature, like a bowl, gives a minimum. Negative curvature, like an upside-down bowl, gives a maximum. Simple case 1 constraint. When m equals 1, the bordered Hessian reduces to B equals a 3 by 3 matrix with 0 in the top left, G sub x and G sub y across the first row, G sub x, F sub Roman 20, F sub xy in the second row, and G sub y, F sub x, F sub y in the third row. Computing the determinant of the 2 by 2 and 3 by 3 leading principal minors yields the test. Practical tip: in many engineering exams you only need to check the sign of the reduced Hessian, the part of HF projected onto the tangent space of the constraints. This can be obtained by eliminating the multipliers using the linearized constraint equations. If the bordered Hessian is singular, determinant 0, the test is inconclusive. You must resort to higher-order derivatives or problem-specific reasoning. Explanation: typical exam questions and how to attack them. Short answer: find the stationary points of f of x comma y equals x squared y subject to x plus y equals 4. Step 1. Write L equals x squared y plus lambda open parenthesis x plus y minus 4 close parenthesis. Step 2. Compute partial L partial x partial L partial y partial L partial lambda. Step 3. Solve the 3 linear non-linear equations. Step 4. List the points. No need for second-order test unless asked. Long answer: minimize c equals 2x squared plus 3y squared plus z squared subject to x plus 2y plus z equals 10, and x minus y equals 1. Determine the nature of the stationary point. Step 1. Form L equals 2x squared plus 3y squared plus z squared plus lambda 1 open parenthesis x plus 2y plus z minus 10 close parenthesis plus lambda 2 open parenthesis x minus y minus 1 close parenthesis. Step 2. Derive 5 equations: partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, and the 2 constraint equations. Step 3. Solve, often by first using the constraints to express two variables, substitute, then solve for the remaining variable and the multipliers. Step 4. Obtain the point. Step 5. Build the bordered Hessian size 5 by 5. Step 6. Compute the relevant principal minors. Apply the sign rule to conclude that it is a minimum. Conceptual, state Lagrange's multiplier theorem and explain in words why the gradients must be parallel at an extremum. Trick question: find the extremum of f of x comma y equals xy subject to x squared plus y squared equals 0. General strategy checklist. Step 1. Write down all constraints clearly. Step 2. Form the Lagrangian with a separate multiplier for each equality. Step 3. Compute partial derivatives, double check signs. Step 4. Solve the algebraic system. Start with the simple constraint equations. Step 5. Verify each solution satisfies every original constraint. Step 6. If the question asks for nature, construct the bordered Hessian or reduced Hessian. Step 7. State the final answer, points, multiplier values optional, and whether it is a maximum, minimum, or saddle. Time-saving tip: for two-variable one-constraint problems, you can often avoid the bordered Hessian. Substitute the constraint into the objective to get a single variable function, then use the ordinary second derivative test. Marking scheme hint: examiners award marks for a correct Lagrangian, B correct first-order equations. C solving algebraically, D checking constraints, E second-order test if required, F clear interpretation of the result. Common pitfalls and exam tricks. Redundant constraints. Two constraints may be multiples of each other, for example, x plus y equals 5 and 2x plus 2y equals 10. The Jacobian loses rank, causing the bordered Hessian to be singular. Before forming the Lagrangian, simplify the list of constraints. If they are dependent, drop the redundant one. In the exam, quickly test linear independence by checking if one can be expressed as a linear combination of the others. Degenerate Hessian. The ordinary Hessian of f may be singular at the candidate. For example, f equals x squared at x equals 0. The bordered Hessian may also be singular, making the second-order test inconclusive. Use alternative reasoning. Substitute the constraints and examine the reduced one- or two-dimensional function directly. Look at higher-order derivatives or consider the geometry of the problem. Missing a sign. The condition gradient f plus lambda gradient g equals 0 is easy to mistype as gradient f minus lambda gradient g equals 0. This flips the sign of lambda and leads to wrong solutions. Write the Lagrangian first, then differentiate. The sign of lambda follows automatically. Treating lambda as a variable to eliminate too early. Trying to solve for lambda before using the simple constraints can produce messy algebra. Solve the explicit constraint equations first. Express some variables in terms of others, then plug into the gradient equations. Assuming a single stationary point means global optimum. For non-convex f or non-linear constraints, multiple stationary points may exist. After finding all candidates, evaluate f at each and compare values. Use second-order test to discard saddles. Forgetting to check feasibility. Algebraic manipulation can produce extraneous solutions that do not satisfy the original constraints, especially when squaring both sides. Always substitute back into every original constraint before accepting a solution. Overlooking inequality constraints. The theorem as stated works only for equalities. Many exam problems hide an inequality, for example, x greater than or equal to 0. If an inequality appears, treat it with the Karash-Kuhn-Tucker conditions, or check the boundary separately, set the variable to the limit, and reapply Lagrange. Bordered Hessian sign pattern confusion. Mixing up the alternating sign rule for minima versus maxima leads to wrong classification. Memorize a short mnemonic. For a minimum with one constraint, the 2x2 principal minor must be negative, the 3x3 positive, and so on. Write the pattern on the back of your rough paper. Exam tricks. Quick substitution. When the constraint is linear, for example, a x plus by equals c, solve it for one variable and substitute into f. This converts the problem to an unconstrained single variable optimization. Fast and safe. Zero multiplier clue. If a constraint does not appear in the final equations, its multiplier solves to 0. That constraint was inactive, often a redundant or boundary constraint. Mention this in your answer. Symmetry shortcut. If the objective and constraints are symmetric, for example, swapping x and y leaves everything unchanged, the optimum often occurs at the symmetric point. X equals y. Use this to guess a candidate and then verify with the Lagrange equations. Check extreme cases. For problems with a circle or sphere constraint, examine points where the gradient of f is radial, parallel to the position vector. This aligns with the multiplier condition and can give the answer instantly. By keeping these pitfalls in mind and applying the shortcuts, you can avoid common mistakes and earn full marks even under time pressure.